All right. I'm excited to welcome our next speaker, Bin Yu, here from Berkeley, who's going to talk about stability and convergence trade-offs of iterative optimization algorithms.
Thank you. I'd like to thank the organizers for having me. And this is joint work with Yuansi Chen and Chi Jin, both sitting there. So I want to first give you a little bit context of why we end up with this project. So my group has been doing a lot of data, scientific research, and data-driven discoveries. And I have been going around for the last 2 years, really advocating 3 principles for data science: predictability, stability, and computability. And predictability and computability very much already embedded in machine learning. And stability, I see it as a way to bring back statistical inference, and also just for interpretability and scientific reproducibility. So this is a picture in my book in making with my student, Rebecca Barter. Try to really make stability kind of the roots of data analysis, and with computability as the trunk, and prediction and other data results, and with the soil as data. So my angle to stability is actually very applied, and it's really, I think it's very, very fundamental for data-driven knowledge discovery. And if I really want to be highbrow, I have a quote from Plato on the stability of knowledge. So this is given to me by a philosopher friend from Northeastern. So in this dialogue called Meno, Plato was expressing his opinion that that's why knowledge is priced higher than correct opinion, which can change. And knowledge differs from correct opinion in being tied down. So tied down, I think, stable. So this is self-evident. About 5 years ago, I started working on unifying stability from different subjects and statistics, and also dynamic systems and numerical analysis. It's really a platform to integrate myriad of works in the literature and to develop new methods. And at the time, there was a lot of coverage of false discoveries. It's really driven by the need to do scientific reproducible research and for interpretation. And now we're moving forward. Actually, it's really very, very useful for intervention design. So you have predictive analysis, you add stability, and you want to have targets for experiments to carry out. So reduce the cost than searching all over the place. And we already heard Mac's very nice overview talk that stability, not just in this modern algorithm stability results, actually we can go back to central limit theorem. It's very much one version of central limit theorem proof is the Lindenberg swapping trick. So you basically remove and change one variable at a time, and you have some bound, very much in spirit as what Max was doing, to prove there's a limiting universal result for this normalized IID random variables. And if you don't use Gaussian random variable as the replacement, you can actually have ODE, and that characterizes the distribution has a unique solution, which is normal distribution. And the stability technique is also much in the random matrix results in high dimensions. Also, it's underneath it's a stability result. So it's very fundamental for data analysis, and also we can see fundamental for foundations of statistics. So stability principle, try to unify, say you define your appropriate perturbation to data and models, and you define a stability measure. And we've seen a lot, it's like perturb one, that's called jackknife in statistics. You change one data point at a time. And in practice, we perturb by cross-validation, bootstrap, and subsampling, and also want to unify things. Peter Abuse group actually, they have also data come from mechanistic simulation data. That's also a form of perturbation to data. So it's really try to put it together. And we do a lot of my like homing in on stability come from the practice and building stability into a lot of predictive algorithms. For this work, we have stability-driven work for development biology to figure out what are the pre-organ regions using spatial gene expression patterns. And there's other work we've been adding stability to LDA. And so when we're ready, so theoretical analysis is very much a component for my group to solve real problems. We have algorithm, we have domain knowledge, and another bit is actually practice-driven theory. So when we're doing that, it happens, I think, Moretz, interviewed at Berkeley. And that's the work Moraz, Ben, and Uram very much become on my radar. And then approach Yuan Si to start on this project, which is try to, and then Chi joined later, that this algorithm stability and computability are use convergence rate as a surrogate. If you really want to go by Turing machine, all that, that's not quite tractable. So we try to really connect this algorithmic stability and practical computability through convergence rate. And there's equivalence made already, generalization. So generalization error is not exactly as what I want in practice yet, which is good prediction. But it's close, right? Because here, generalization error doesn't deal with the model bias. And in practice, you really want to have something on that. So we're not exactly there, but the three components are there already. So for the rest of the talk, we're going to try to push forward this stability and convergence line of research to have a trade-off between stability rate and convergence rate. And in some sense, we're returning to a theme was already in Berkeley and Alice's paper. They kind of alluded to this variance and bias trade-off in their paper. And we kind of return that in the stability framework. And then we combine with statistical minimax rate, use Lecomte's method, and bring in statistical lower bound and combine, have a new class of algorithms. And we can talk about lower bound of convergence. And the last bit is really try to do upper bound, see convergence, uniform convergence, doesn't depend on the iteration, and can be quite inaccurate in early beginning of iterative algorithm for estimation. So here are some notations. I think I'm consistent with the notation of the last speaker with S, which is the sample you have, ID. And you can see all this analysis will be more challenged if you remove the ID assumption, right? We're really having very nice mathematical structure here. If you have time series or something like, a lot of the devices have to change. And you have population risk, which is unknown, R theta. Instead of W, I have theta. Last lecture has W as the unknown, I have theta, so switch. And the empirical risk, which is known, which is the training error. And S is the sample. And we really want to minimize or try to reduce the excessive risk. Right here, it's like, can you use the data the best you can if you know the oracle theta 0, which is the closest your family of models relative to the true distribution. Okay, so hidden in theta hat S is also an iteration T, which I will bring it out sometimes, but usually keep that in mind. So it's a method with a particular iteration. And theta S tilde is actually the empirical minimizer. And the last equation really tells you it's pretty easy. You add a term, you subtract a term, you add a term, and subtract term. And the last bit is less than or equal to 0 because you have theta tilde, which is the empirical minimizer. And if you take the oracle estimator on data, that will be higher than theta tilde S. So that's less than 0. So therefore, the first term is generalization error, or later we'll show is bounded by stability. Stability is really a positive way of saying a variance or uncertainty. And here we don't have to deal with L2 error, but this is nevertheless a measure of change when you change the data. And it's already the most, I think, oldest probably form of complexity measure, which is the variance. And this is like, you can think of this as a computational variance because all kind of a lot of crunching, moving data around, which was not conceivable 50 years ago to calculate stability measure. And the bias is relative to the best oracle model you have. So it's kind of, I would say, not systematic bias, but a model bias relative to the best you can do within the class of models you are entertaining. So very much it's this variance bias trade-off, which is very, very important for high-dimensional statistics and machine learning. So if you look at the first term, historically, we already have ways to upper bound the generalization error, right? The first is uniform convergence bound. Actually, I did my thesis like 30 years ago on doing this VC bounds under dependent data. That was, we call empirical processes. That was the name. And David Pollard at Yale, there was a lot of people doing that. And later we moved to random micro complexity. Symmetrization was the key. And then later on in the boosting literature, there was this margin bound by Shapiro et al. Right? They now have a book. So that's another form of bounding the generalization error. And now we have algorithmic stability bound, right? In the talk, we have seen TON for stochastic gradient descent, and also gradient descent basically was also in Morat's paper already for that. Okay. And if we take what I did in 2 slides ago and bring in stability, which have been talked a lot earlier today, then we bound generalization by stability, and we bound the other term I call the bias by we call optimization. So we have this trade-off as upper bound. It's the excessive risk decomposition. If we turn it around, write it the other way, it's the same inequality, because we somehow want the lower bound to appear on the right-hand side. We can follow the more statistical thinking of minimax, Lacombe's method, to construct 2 distributions, which kind of the hardest for the subproblem, and you can have a lower bound. So you have 3 terms, right? So the right-hand side term, I can dip into statistical minimax literature and prove a lower bound depends on the sample rate. That had nothing to do with the algorithm. And stability, I have an upper bound. Move it around to the other side becomes a lower bound with negative. And then suddenly I have a lower bound on the optimization term. Okay. So for a particular example, you can show for convex smooth loss, the lower bound use Lacombe's method by constructing special distribution. And you can have 1 over square root of n as the rate. And we are interested in the trade-off of the 2 terms as a function both t and n. So in addition to this trade-off, I think we believe the first time to be able to show a stability bound for natural accelerated gradient and heavy ball method. And they are kind of second order method, and I have a star there because we need even in the quadratic case, or piecewise quadratic case, was quite delicate. I was reading Yuan's proof last night, was like quite heavy use of analytical results. And you can see that the stability upper bound for gradient descent and stochastic gradient descent is linear in the number of iterations, and for natural accelerated gradient is t squared. So stability is less stable, but also converges faster. So as a result, you can take t equal to square root of n for the top, you get optimal rate for estimation, and you can take t equal to n to 1/4, you still get the same rate. So it's just like they trade off differently, and you adapt to the problem by early stopping in different ways. Okay, so you cannot say which one is better, at least in this idealized situation. But in practice, people like slower algorithms. Somehow you have more asymptote, kind of low flat area, so maybe data-driven method, finding that early point is probably more stable. When things move very, very fast, things get unstable, so finding the sweet spot might be more challenging. But in terms of theoretical rates, they both optimal, just by choosing different stopping point.
The stability bound is for the exact step sizes that appear in Nesterof's method, or is it no matter how you choose the
I think it's the exact step size.
Because it could be that somehow you can make the step size smaller,
Yeah.
it's more stable, and still accelerate.
This is the vanilla.
Vanilla or
Yeah.
Nesterov.
Yeah, that's another. A lot of the bound, we're not talking about the step size, right? That's another, you can make a third argument to say that how does that include it depends on how that fast. I'm sure you could have different stability rate result. Okay. And the second thing I want to talk about is convergence lower bound for stability. I already hinted to, right? So you can show that for convex smooth loss, the convergence rate, so you keep the stable, the rate of stability for algorithm, and you put them into the same class. You can show that then the optimization bound is lower bounded by 1 over STN. So this saying something conceptually very heuristic, very make a lot of sense is stable algorithm cannot converge too fast. And here is an example that you have a lower bound, as I showed you for the particular case, and you move the stability upper bound, ST over N, to the other side. And if you choose STN properly, you get a lower bound on the optimization convergence rate. So this is related, but not the same as earlier class of algorithms in the literature, right? The first order deterministic algorithm in Nomorowski and Udin, they basically say if you have access to the first order information, then for this class of algorithm, you cannot converge faster than a certain rate. In the Agoraro work, they have a stochastic version of that because stochastic, they have to put constraints on the second moment of the gradient. And we have is really a stable algorithm. We control the stability of the class algorithm. And it's just a different way of looking at the convergence rate. And this is more statistical in some sense because stability is very much embedding variance in statistics. And for this case, they are the same, right? The question is, I don't think they have to be the same. Depends on how you set out the class. For gradient descent, right, the upper bound base is already in the paper of Morris-Ben and Uram. And we also know a convergence upper bound. And our lower bound really say that for this new class of algorithms, we know that the convergence rate cannot be faster than 1 over T. And as I alluded to earlier, we were able to show for quadratic loss and piecewise quadratic loss, non-zero accelerated gradient method and heavy ball method with fixed moment parameter, upper bound, and putting together, we have this table. So the two red ones we believe to be new, but under the somewhat restricted condition on the loss function. So you now, from statistical considerations, you end up with convergence lower bound, and you're putting algorithms together from estimation point of view instead of how they reach to the first order information. So the last message of my talk is really now let's compare stability versus uniform convergence upper bound, right? So I kind of came to machine learning. The first paper actually I did was with Peter Billman was on bagging, analyzing stability or instability of bagging. We went into this more refined empirical process result and showed that bagging is reducing variance. So that was actually my first encounter with machine learning and turned out to be actually stability related because Leo Breiman really bridged statistics with machine learning and kind of, in a way, Berkeley is so good with this connection with Leo's vision with Peter and John Rice hired Michael Jordan 20 years ago. That's why Berkeley had such a tight connection between machine learning and statistics. So Leo was very concerned with stability and reduced stability by bagging. And then I worked on boosting, same with Peter Billman. And we did a very special case showing that the number of steps, when you increase the number of steps for boosting, your complexity actually asymptote. That's exactly what in the new work we can see is that in the beginning it's number of iterations, and then you don't keep going up the complexity. You have to use now the uniform convergence bound. So we have two ways to bound this generalization error. And in the beginning, think about it, start from 0, a fixed point. You're not really able to explore the whole space. So your complexity is not really reflected by the VC class of the dimension. You're really in a very local situation. And uniform convergence for the large scale problems it's seemed to be uniform convergence bound, has no t in there, saying that it's square root of d over n. But the stability really says that it's t, for example, gradient descent over n. When t is very small, it's much, much faster. So I just want to show you that these bounds really capture what's going on in some examples. So you should take these plots as qualitative, because we actually, in the plots, calculated using data the stability. So it's not the bound, it's really the stability calculated through the definition and also optimization with one run. But you can see that it's linear. This is log steps, and the purple is the uniform bound. It doesn't change. And for small-scale logistic regression problem, the generalization area is controlled by optimization. So that's the main concern. You do want converge fast. That's what you do in all these statistical general linear models. You really basically let it to converge, and then you get the fish information out. And the stability bound is more relevant, but it's not dominant. So it doesn't matter too much which one you use, because it's dominated by the optimization error. And you can see the Nassarov, it's a different rate of convergence. When you go to large-scale problems, as I was alluded to earlier, you're really in the beginning exploring much smaller set of the space. So the uniform convergence bound is just it's like too big and doesn't really capture what's going on. So when you look at large-scale logistic regression problem, again, you see that the test error is the dark, like the thicker blue for the first plot for gradient descent, and the other one is the optimization error. And because gradient descent converges slowly with the iteration number we plotted, they pretty much follow each other. But for a faster algorithm, as nested accelerate gradient, even with the iteration duration we showed you, they part their ways. So for this case, the uniform convergence bound is just stay the same. It's not sensitive to this change. Things are actually coming back now. And the stability bound is able to follow qualitatively this turning back. So for large-scale logistic regression problems, stability is sharper and more indicated on the behavior of the test error, as I was now just plotting them together to see that. The stability measure, this is not from the bound, theoretical bound, is from the calculation, but I can see that it's linear. And it's not exactly linear because the bound is exactly linear. And this is to show that the stability bound is able to give you the sweet spot to early stop, even though it might be a little early because it's still an upper bound on the stability. So to summarize, so our stability were very much motivated with the practice of the group using stability, adding stability to prediction error. Prediction error we use as a goodness of fit, and we have been adding stability in a variety of problems in document summarization, genomics, and neuroscience, and both data perturbation and model perturbation. And that led us to the stability result we presented here relative to computation, like computation convergence rate. And we emphasize the trade-off between stability and convergence rate, which is especially relevant for large-scale problems. And we're able to get new stability bounds for natural accelerated gradient descent and heavy ball method under quadratic and piece by quadratic loss function. Even they are quite delicate already. And we do believe the stability bound can be used in practice, especially early for faster algorithms. You have to do all this as a way of calculating complexity. And we're still working on the final version of the paper. We hope we'll be able to upload it in 2 weeks. Thank you.
Time for some questions. Actually, I had a question about the stability bound for Nesterov. Does it carry over to just plain momentum when you have just extra term with some coefficient? It should be easier to analyze in some sense.
I think so, because the heavy ball method is a fixed momentum.
So, and you have for any choice of the momentum coefficient, you could give me stability.
I think, yeah. But it's quite heavy. We have been, this has been stopping us for like year two.
It's kind of, it gets messy.
Yeah, so that's why the whole project being stopped, and
I'm glad you're doing this.
but eventually we still didn't get where we wanted to be, but it's time to, at least maybe other people can come in and do the more general case. That's kind of, so stop like a year and a half on this. We're stuck on this for a year and a half, at least.
I'm so relieved because I was thinking about doing the momentum analysis, and I was like, probably somebody else is going to do it.
Yes. Young people can do it.
So yeah, we just so we didn't prove the general case. It's a restricted case, so that's enough. We can apply the lower bound. So yeah. So
Quadratic and piecewise quadratic, but still there.
Oh, it only applies for quadratic functions.
Oh,
yes.
piecewise quadratic a little bit.
And then it's enough in the convex loss case that we can apply the lower bound and exceed the trade-off.
But even there was was not trivial. Yes.
It's easy to estimate the stabilities when you run in algorithms.
Yeah, because you just perturb the data. That's what we use in practice, right? We've been adding things like that on top of cross-validation. But you have to decide on your version of, all the theoretical analysis is on perturb 1, I call jackknife. But in practice, we often perturb more than that. And we have, I think you and Ras have some early result on, we call ESCV. It's a version of adding stability to cross-validation. Yeah. So in practice, it's called DD1 jackknife. That's people actually traditionally have used. It was proposed in the 40s in statistics, and people use it to estimate variance and also bias. So it's kind of, we had a parallel version of all of that, but not using the modern technology in statistics. And people didn't look at the objective function, they look at parameter estimate. So we use that a lot in our groups, like data-driven research. But you have to be careful about what version of stability and loss you choose. But one thing is that we like to circle back to the motivation that hasn't happened yet. Yeah. To see what this theoretical result can help us to do the practice. There's easily a gap. Yeah. Exactly the time. Thank you.